do 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 do. Alright, we're done with intermission. If you're starting with this video, go back and watch the previous video before you watch this one, because we are calculating delta G using one of the several different forms that I've shown you. Now we're going to talk about if we are not at standard conditions. If we're not at standard conditions, we're going to have to use a delta G. We're not solving for delta G naught, delta G with that little with that degree sign. We're solving for delta G, for free energy, when we are not at standard conditions. So for example, the one method of synthesizing methanol involves reacting carbon monoxide with hydrogen gas. We're asked to calculate the free energy at 25 degrees Celsius, and our concentrations of these gases are not 1 molar, or not 1 mole, and therefore we are not at standard conditions. So we need to calculate delta G using the formula that does not involve standard conditions. And that's delta G equals delta G naught minus R times the temperature in Kelvin times the natural log of Q. So let's start with finding out what Q is. Q is the easiest thing to find. Remember that as we move towards equilibrium K, when we're at equilibrium K will equal Q. But since we're not at equilibrium yet, we can use these values for the pressure of these two gases to determine Q. And since we're producing methanol, which is a pure liquid, a pure substance, it will not participate in our Q. So whenever we come across that, we're just going to put 1 in its place. So Q equals the concentration of methanol divided by the concentration of carbon monoxide times the concentration of hydrogen squared, because we have to square the concentration of hydrogen since it has a coefficient of 2. I already said methanol is a pure substance, pure liquid, so we are not going to include it in this Q, so we're going to sub in 1 for methanol. And we can use the pressures given to us in this formula, in this problem, to determine the concentrations, or to sub in for the concentrations of these two gases. So let's go ahead and plug those in. So for carbon monoxide, we're going to do 5 atmospheres. And for hydrogen gas, we're going to do 3 atmospheres. Now Q is a naked number. It has no units, so I'm going to leave them off when I do this calculation. 3 squared is 9. 9 times 5 is 45. So we're looking at 1 over 45. Or as a decimal, comes out to be 0.0222222222222. All right, so now we have a value for Q. T was given to us up here. We've got a temperature reading, and that's 25 degrees Celsius. We're not going to use that. We've got to change that to Kelvin. So 25 plus 273 is 298. We need an R. Well, we take that off of your givens. It is 8.31 joules per Kelvin mole. Lastly, we have delta G naught, or the free energy at standard conditions. Normally, when you'd receive this on an AP exam, they'll give you this value. However, if we're working with our homework, or we're working, from our packet like we're doing right now, we would need to look up the delta G for each one of these from a table in the back of the book. So if you turn in your books to page 1041, you'll find a table with the heat of formations, the free energy of formations, as well as the entropy of various compounds. So we actually do have a table that will allow us to calculate delta G using our Big Mama equation, the sum of the products minus the sum of the reactants. So it will be the heat of the free energy of formation of methanol minus the formation of the free energy formation of carbon monoxide plus the free energy of the formation of hydrogen. Well, hydrogen's elemental, so we automatically can say, nay, that is going to be 0. So let's plug that in. If we look up carbon monoxide, it is in the second column. Delta G is going to be negative 137.2, so we can plug that in as well. And just above it, if we look up methanol, we have two here. We can either do gaseous methanol or we can do methanol as a liquid. We look at our problem, we were producing methanol as a liquid, so we have to make sure we grab the correct one. So it's a negative 166.23 kilojoules per mole. So we plug that in as well. Now all that's left is to do the math. 166 minus a negative 137 is going to give us a negative 29.03 kilojoules per mole. So let's not lose sight of what we're doing. We're going to take this value now and plug it into this formula with all these other values we found. Now right off the bat, you should be able to look at this and say something's not going to work out here because I have negative 29 kilojoules per mole, 8.31 joules per Kelvin mole, Kelvin, and then something with no units. Kilojoules and joules aren't going to cancel each other out. I need to make sure I have something that's going to be mathematically sound. So I'm going to either have to change this value, my R value, into kilojoules, or I'm going to have to change my kilojoules into joules. Personally, I prefer to make the bigger value, so we're going to change this 8.31 into kilojoules. So we're going to divide this by 1,000, and we're going to get 8.31 times 10 to the negative 3 kilojoules per Kelvin mole. So again, if you were confused about why we changed this to kilojoules, if we had left this as joules, Kelvin would have canceled Kelvin. This has no unit, so that wouldn't have come into play. We would have been left with joules per mole, and we would be subtracting joules per mole from kilojoules per mole, and that's not mathematically possible. So we have to make sure our units cancel out. Units are very important, so pay attention to units. They are our friends. They tell us what to do. So after we've plugged in all these values in, we can just follow our normal mathematical operations, and we would find that delta G, or the free energy of this reaction, is a negative 38.5 kilojoules per mole. So therefore, this is a spontaneous reaction. If you were following along very closely, you'll notice that the sign that I changed the signs here is because I copied the formula incorrectly. It's delta G plus RT ln Q. This doesn't become a minus until we're talking about at equilibrium, when it's delta G equals negative Ratlength. Sorry. I will apologize 1,000 times. I am so sorry. I copied the formula incorrectly. This is correct. It is supposed to be a negative 38.5. Speaking of Ratlength, let's do a problem that involves it. Exercise 15 in your packet, calculating the free energy and equilibrium. We're given a problem and asked to find the equilibrium constant for this reaction at 25 degrees Celsius. Well, right off the bat, you should be able to look at that and say, that's not 25 degrees Celsius, that's 298 Kelvin. Also, you'll notice that up here that I pretty much copied this directly out of your packet. This symbol here should be an arrow. Every now and then the computer gets a glitch in it, and for whatever reason the PDFs have numerous errors in them. For example, some of the formulas say delta G equals delta GE plus RT ln. That GE, that E should be the not symbol. I do not know why it glitches this much. I will address this at the next conference with the VAST people, but for right now, that omega symbol should be an arrow because this is a balanced reaction. So let me go ahead and fix that for us. So as I said, we're at equilibrium and we're asked to calculate the equilibrium constant, or K. So this is the time we're going to use delta G equals negative Ratlength. So R is a constant, we're given that. T is a temperature, we're good. K is what we're solving for, but delta G, not the standard free energy, we're not given. So we need to be able to calculate delta G from just the information given to us. So we're going to have to go through a couple steps to do that. So first, delta G equals delta H minus T times delta S. So if we find delta H and delta S, we can find K for this equation. So let's start with delta H. So products minus reactants. So 2 times iron 2 iron 3 oxide minus 4 times iron plus 3 times oxygen. But oxygen is being formed, so delta H is 0, so we can take that out. So it's really just iron 3 oxide minus iron. Let's plug those values in. Even sweeter still, iron is also elemental, so it's also 0. So this is just 2 times the heat of formation of iron 3 oxide. So we would just double that and get negative 162 kilojoules per mole. So we've got delta H, now we got to get delta S. It's another Big Mama equation. Delta S equals the sum of the products minus the sum of the reactants. So we're just going to plug in our formula just like we did before. So now we've got our formula in there. We can plug in our values and womp womp womp. These are elemental, but remember with delta S that doesn't matter. So we actually do have some values we need to plug in. So once we plug those in, it will look like this. And once you solve all of that out, you'll find that delta S equals negative 543 joules per mole Kelvin. You got to make sure you follow those units down. All right. We now have delta S. We have delta G, or delta S and delta H. Let's find delta G. Negative 162 kilojoules per mole minus 298 Kelvin times negative 543 joules per Kelvin mole. Kelvins cancel kelvins, kilojoules per mole minus joules per... No, can't do that. I've got to switch this. So I'll divide this by 1,000, giving me 0.0543 kilojoules per mole. Once I do that, I can find that delta G equals negative 1,495.07 kilojoules per mole. All right, but now let's not lose sight. We were asked to solve for the equilibrium constant, so we're going to take this value now and plug it back into negative Ratlink. So this is our G naught. We can plug it in up here, and when we do that, I'm going to get rid of all this down here, so if you need it, you need to pause it because it's about to go away. It's better. All right, so now we've got our G naught, our standard free potential, our standard free energy, equals negative Ratlink. Let's plug in some values here. First off, let's plug in T. Temperature is 298 Kelvin. R is the gas constant, 8.31 joules per Kelvin mole. K is what we're solving for, so we're good on that front. Let's just make sure our units here cancel out. K cancels K. Kelvin cancels Kelvin. I'm left with joules per mole. I would divide that by kilojoule. I would divide kilojoules by joules per mole. I can't do that. I've got to make sure my units are going to cancel out. So I need to make this negative 8.31 joules per Kelvin mole. I got to make it into kilojoules per Kelvin mole. So you guessed it, multiply or divide by 1,000 again. So negative 8.31 times 10 to the negative third. I abbreviated it because space is running out. Now all of my units will cancel out. I can do this mathematically, and what I'll end up with is 601.75 equals the natural log of K. If I raise E, because that's the opposite of ln, if I raise E to this value, I'll end up with K. And if you plug that in the calculator, you end up with an overflow. So I personally don't really know what to do with that number. If I receive that as an answer on my FRQ, I would think I had done something wrong. However, I'm telling you right now that we did this problem 100% correctly, and I would simply write my answer as E to the 601.7, because that's the only way I could see to write an answer this large. It is a massive number. So K equals 601.75.